Next up is Stijn Cambie from, I'm not going to pronounce his Stijn, sorry, I really can't pronounce the name of that university. And he's going to tell us about the general problem of Erdős and Nešetřil. So whenever you're ready, go ahead.
Yeah, well, it's not just about me being ready, it's also about the audience being ready, because we just had a talk of 40 minutes. So.
Yeah, I think it's also fine if we want to do like a 2-minute break or something, and yeah, I can do mine in a bit shorter as well, and we have a bit of a break.
Yeah, but I think I skipped parts, so it will be a bit shorter, so that at least people can follow, and I put some break inside as well.
Nice.
We will see. And I had to do one small correction in the title. Actually, it's a general problem and not the general problem, because Erdős and Nešetřil had multiple ones. So
this is the most important one, I guess.
Yeah, you can discuss about this. So it's like, yeah, that's also like about the own taste. But I just will start. So thanks for the organizers to invite me, and I'm happy to speak about a general problem of Erdős and Nešetřil and some related problems. And for the people who are interested in it at the end, so this is based on a joint work which is at Archive with Wouter Kames van Batenberg, Remy de Johannes de Verklos, and Roos Kang. And to start with a slightly easier to state problem, I would like to mention the degree diameter problem, which will be pretty similar to the problem of Erdos-Nešetřil I will be speaking about. This question asks about the maximum order of a graph given some fixed diameter and maximum degree. So once you know the diameter and the maximum degree of a graph, it's pretty easy to see that there is an upper bound, so there is also a best value, and the degree diameter problem asks about the best or the maximum order in general. And as a small example, or to present the bound, if you look to one local vertex, due to the maximum degree condition, you know the vertex has at most delta neighbors. And each such vertex has again at most delta neighbors, one of them being in the graph already. And you can repeat this up to the point that all vertices are up to distance the diameter of the vertex. So somewhat the best extremal graph, if instead of looking to the diameter, you just say that all vertices are at a distance at most d from a vertex v and the maximum degree is delta. The maximum bound of this will be attained by a tree looking like the one on the left, which is a rooted tree with radius d, such that every non-leaf has degree exactly equal to delta. And for such a graph, it's easy to compute the order. So the formula is written here, and it's bounded by delta to the d plus 1. So of the order delta to the d. And in certain cases, this so-called Moore bound is attained. So for example, when the diameter is 2 and the maximum degree is 3, an upper bound was attained by this tree, which has 10 vertices. And indeed, for example, the Peterson graph is a graph for which this is attained. So this graph it's a tree regular, and it has diameter 2. And note that it's, if you pick any vertex, you can find with a search a spanning tree starting from this vertex, which is isomorphic to the tree. But in general, this bound is far from or is not attained. So there are only a few cases for which the Moore bound is correct. And so it's very hard to find the exact bound. And the problem of Erdős and Nešetřil is about a similar question, but instead of looking to the diameter of the graph, we will be looking to the diameter of the line graph. I hope everyone knows the definition of a line graph. So if you have a graph, you consider all edges as being vertices, and two edges are adjacent if they share a vertex in the initial graph. So then the question of Erdos and Nešetřil asks about determining the smallest integer h such that every graph G with maximum degree delta and size h contains two edges such that the shortest path joining these edges has length at least t. And it's maybe the question is not posed that elegantly, so to pose it a bit more elegant or at least shorter, an equivalent form is to ask about the maximum size of a graph G with maximum degree delta, for which the line graph has diameter t, which implies that every two edges can be connected with a path of length at most t minus 1. And this maximum size will be h t of delta minus 1. And according to Erdos, as written in his paper from '88, so almost a bit more than 30 years ago, this problem would be mainly interesting if there is also a nice expression for ht of delta. Okay. So then this is pretty similar to the degree diameter problem. And in particular, it's again pretty easy to see that there is an upper bound. And this upper bound will be smaller than 2 times delta to the t. So somewhat you have an analog of the Moore bound. And the intuition behind this is also similar. So looking to the picture below, if we look to one edge, for example, the one between the two red vertices, there are only at most 2 times delta minus 1 edges who share a vertex, because both vertices have degree at most delta. So there can be delta minus 1 additional edges on the left, delta minus 1 on the right. And then at distance 2 from the edge, you can have the same. And you repeat this up to the diameter t. And then summing the maximum number of edges at a distance I from 1 to t, you get a bound which is smaller than 2 times delta to the t. So it seems very similar. But in this case, the bound even can be attained. So there are no analogs of the Moore graph. And to see that it's smaller than 2 times delta to the t in most cases, because there is one trivial case in which it's the case. So, but I want to ask you to solve this. So let's look to the easiest case of Erdos-Nešetřil. So looking to t equals 1. So in that case, we are asking the same question with a maximum degree d, and the line graph has diameter 1. What's the maximum number of edges such a graph can have?
You can take something like a star, maybe? Is that the
yeah, that's an example. So,
what size does that have?
Delta.
Yeah.
A complete graph? No, complete graph doesn't work this time. Yeah.
Yeah, so the line graph having diameter 1 implies that every 2 edges share a vertex. So for example, the star would be a trivial family, and analogously to the Erdős-Corrado theorems, we expect the trivial family to be extremal in many cases, and it's actually not a hard thing to see this is the case, with one exception, which is the triangle. So if delta is 2, because then if you would have the star with 2 leaves, we just can connect the additional 2 leaves with an additional edge, because this edge is also adjacent to the 2 other edges. So yeah, just by checking the properties, we have solved Erdos-Nešetřil for t equals 1. But obviously, Erdős and Nešetřil weren't that interested in the t equals 1 case. They were asking about more interesting cases. For example, the t equals 2 case. I guess this question will be too hard to pose here, but so it's the same question with the line graph having diameter 2. And I do not expect anyone to solve it, except if the person knows the result from the literature of having worked on it in the past, but also in the past they first considered an easier case, which were bipartite graphs. So the bipartite case is easier and was solved in a pretty short and neat theorem by Chung, Giarfas, Tusa, and Trotter. So they proved if you have a bipartite graph with maximum degree delta, for which every two edges share a vertex or are connected by an edge, there can be more than delta squared edges. And there is only one unique extremal graph, which is the complete balanced bipartite graph on two delta vertices. So for example, when delta is 5, it's presented here. So it's easy to check that there are delta squared edges, because you have edges between the delta vertices on top and the delta vertices at the bottom. And every two edges share a vertex, or they are spanning 4 vertices which induce a C4. So there is no induced matching on two edges. And they proved this. But not only did they prove the easier case for the bipartite graphs, they also solved the general case. And in this case, the maximum is 5/4 times delta squared. I won't mention anything about the proof, but the main intuition behind it is, again, there are some extremal graphs which are nice. And in this case, these are the blown up C5s. So you start with a C5, and you replace every vertex with an independent set of order delta over 2, possibly with some rounding. So in the two pictures on the left, it's presented for delta equals 4. So you have a pretty regular construction. Every independent set of the blow up has order delta over 2. On the right, it's with an odd maximum degree, so maximum degree 5. So you have 2 independent sets of order 3 and 3 of order 2. And vertices in the independent sets are connected precisely when the original vertices relating to the independent sets were connected in the original C5. And as you may notice, for delta equal being odd, this bound is even not attained. But those are the two extremal graphs. So one could expect us, Chung, Giarfas, Tusa, and Trotter, solve the problem for t equals 2. The next step would be to solve t equals 3 and higher. But actually this did not happen, because there were other cases which were hard and interesting for t equals 2. So note, in this case, if you look to the line graph of these blown up of C5s, and we take the square, actually we get a clique, because every two edges are a distance, at most 2 in the line graph, so it forms a clique in the square of the line graph. But so instead of looking to such graphs for which we get a clique, we also could look to the clique number. And in that case, we are looking to strong cliques in the graph. And Faudré, Giarfas, Schelp, and Tusa conjectured that the extremal number for this strong clique bound would be the same, and so the blown up C5s would be extremal again. So their conjecture really says if G is a graph with maximum degree delta, then the clique number of the square of the line graph is bounded by 5/4 of delta squared. Note, because we easily can solve the problems for t equals 1, if we would do the same for t equals 1, then the bound delta or delta plus 1 for when delta equals 2 would be again true, and again attained by the star or the triangle. And while the question of Erdos and Nešetřil for t equals 2 was solved already a few years after, the conjecture of Faudré, Giarfas, Schelp, and Tusa is actually still open, or it's not proved, because the best bound known up to now is the one from Farron and Postel, which proves that it's at most 4/3 times delta squared. So there is still a gap of delta squared over 12, so which is already a big challenge to improve. But there are a few cases in which it's known. For example, if the graph is C5-free, so for example, a bipartite graph is C5-free, then it's known that the clique number is of the square of the line graph is at most delta squared. So this generalizes the bipartite case, and it's proven by Wouter, Ross, and François Pirot. And if the graph is triangle-free, then the bound 5/4 delta squared is known, and so in that case, the conjecture of Faudré et al. Is proven. So this is the state of the art of this variation of the problem for t=2. And there is also another one, which is pretty famous and also called the conjecture of Erdős and Nešetřil, because they stated it in a different paper. In this case, instead of looking to the clique number, they look to the chromatic number of the square of the line graph. So note that the clique number is a lower bound of the chromatic number. So this is a harder question. And the chromatic number of the square of the line graph is called the strong chromatic index of a graph. And they conjecture that the same bounds do hold. So if delta is even, the 5/4 delta square would be true. If delta is odd, there is some minus delta over 2 plus 1/4. So this is by the blown up C5 for delta odd. So there is a small difference, and you easily can compute this quadratic polynomial. And if G is bipartite, they also conjecture delta squared would be the best you could do, or it's the maximum number of colors you need to color the edges of a graph, such that any two edges which are at distance at most 2 in the line graph have a different color. Note that the t=1 case is again something we know. Even if you didn't prove Vissing's theorem yourself, you know that the chromatic index, which is the chromatic number of the line graph, is bounded by delta +1. And in this case, many graphs do attain this bound. The best result known for the conjecture of Erdos and Nešetřil, also called the strong edge coloring conjecture, is approximately 7/4 delta squared, which is only asymptotically, so there is still a big gap to improve here. So this is somewhat the history of the results before for t=2. I hope all of you understood up to now. If not, feel free to ask a question, because I think it's a good point to have a break. So I can see from this distance if everyone's brain is still working, so it's a good point. And I will test afterwards. Any questions?
I was wondering, so there's a better case for the bipartite graphs for t=2. Does this sort of generalize for larger t, or maybe not for bipartite?
Wait, the previous questions?
Yeah, so we saw that for bipartite graphs, we do get kind of a nice bound of delta squared.
Yes.
So
for the original question.
Yeah.
Yeah, we will see. So.
Okay.
So the answer is it is, and we'll soon see, because indeed after the break, maybe we can start. We will consider the t=3 case, which is the next case. And in that case, the bipartite case is known, or actually the C7-free case. But before going to there, I just want to be sure everyone woke up after the break and he's ready to solve a specific case for t=3. So if the line graph has diameter 3 and we say the maximum degree is 2, to make it small, what's the maximum size of such a graph? Or what would be the extremal graph? Maybe that's...
A cycle of length, whatever, 9, I don't know. Something
Yeah,
like that.
it's not 9. But
Maybe
it's
7.
Yeah, it's 7 indeed.
Yeah, I'm confused on counting diameters of a line graph.
Yeah, well, so indeed the maximum degree is 2, and because the diameter is finite, we have a connected graph. Maximum degree 2 says it's a path or a cycle, so it's easy to see the cycle is doing best. But actually, if you are having trouble to compute the diameter of the line graph, in the case of a cycle, the line graph of a cycle is the cycle itself. So we just have to look to the diameter of the cycle. So for a C7, the diameter is 3. So if you look to the blue edge, all other edges can be connected with a path of length at most 2. In the case of the C8, the diameter of the C8 is 4. And for larger cycles, it's also at least 4. So these are not fine. And the shortest path between the blue and the red edge, well, there are 2 choices, are of length 3. So this implies that the cycle C7 is extremal and H32 equals 8. So we solved one case of Erdos-Nešetřil for t equals 3, so we might be getting closer. Now, in the case of t equals 2, we have seen that there is a nice construction, the blown up of a C5. But so for t equals 3, has anyone some intuition, some idea, some guess about the extremal graph? Once we know the line graph has diameter 3 and the maximum degree is delta, where delta is more general.
A blow up of a 7 cycle.
That's an option, and at least it satisfies the conditions. And it has been conjectured before. It turned out to be false, and it would also be a big gap with our silly bound, which was 2 times delta cubed, because the blow up of a C7 would have 7/4 delta squared, so it would be only quadratic. But there are 2 examples which are cubic. So actually, the only case we also solved is when the maximum degree is 3. So then the extremal graph is proven with some case analysis. It's depicted below. And for general delta, we do not know the exact answer actually. But there is some conjecture. So together with Wout, Remy, and Roos, we proposed a nice expression because Erdos was asking about one, which would be this cubic polynomial. And we know there are some cases in which equality is attained. And to have some intuition on this, at least we want to have one example which beats, for example, the example of Andre, the blown up C7. And this example is the point line incidence graph of a finite projective plane of some prime power, because you need a prime power and to be sure that such a point line incident graph or the finite projective plane does exist. So for the people who do not know the finite geometry and this construction, there are some handy properties for these graphs. So it is bipartite, it's delta regular, it has diameter 3 and also its line graph has diameter 3. It has guard 6, so no cycle C3, C4 or C5. And it has a size being exactly equal to the number of edges in the T3 delta, where T3 delta is the one as sketched before. So somewhat this seems to be a really good candidate, because one could expect that a regular graph would work and would be the best. And to have just some view of such a graph, here is an example for where you have a projective plane of order 3, so it's a 4 regular graph. And so actually you can notice the 3 T3, 4, where some vertices at this 3 coincide. But actually this is not extremal, because we know we can do at least one edge better, and we couldn't beat the +1. So what we do, we replace one vertex by an edge, and we connect the two end vertices of this edge with initial neighbors of V. So for example, here there is an example with delta equals 4, where the two vertices of this edge are connected to two of the initial neighbors. But we could also have chosen to connect one vertex with 3 initial neighbors and the other one with only 1, in which case we would have a subdivision of one edge. So in particular, if our conjecture would be true, there would be multiple non-isomorphic graphs with the extremal size. But we couldn't prove this. But we could prove the case where there are no C7s. So in particular, we could solve the bipartite case, because Carla is only interested in bipartite graphs. And in that case, the construction is nicely, because it's the extremal size is exactly the one from this pretty regular tree where all vertices have degree delta up to the leaves. We also have some bound in general, so 3 halves times delta cubed. So this is already much better than the trivial bound, but it might be still far off from the real bound, which might be, for example, of the order delta cubed if our conjectures are correct. And I just want to add with some intuition on the bipartite case, because in this case, we seem to have a nice expression and some nice extremal graphs. So for example, when delta equals 3, we know we have this construction, which is a tree, all degrees being 3 up to the leaves. And on the right, we see the extremal graph, which is actually the tree with some vertices, which are coinciding. So you just have to put some edges towards the same vertex. Okay. But now we see that because of the definition, every 2 edges are connected by a path of length at most 2. But so in general, if you would want to check this, you would have to check many pairs of edges. But in particular, if we again look more local, and we focus on one vertex phi and its neighbors U1, U2, and U3, then we know that every edge is connected to these edges by a path of length at most 2. So instead of checking that all edges are at distance at most 3 in the line graph from each other, we also can just look to the distance towards these. And it turns out that this is sufficient. So in that case, we get a theorem where on the one hand, we are asking for weaker conditions, but on the other hand, it's easier to prove, and then the result is a corollary of this. So the theorem states that if we have a C7 free graph, so for example, a bipartite one, with the maximum degree being equal to the degree of our favorite vertex phi, such that every edge in G is a distance at most 2 from any edge VUI, where UI is in the neighborhood of V, then the size of the graph G is at most the number of edges in our favorite tree for during this talk. And one idea or one reason why this is handy, if you are looking for extremal graphs for this with this weaker condition, you can forbid some C3, C5s, for example, or C4, no, not C4s, that's another trick, to make it easier. So for example, here we have our favorite vertex phi, and we have this thick orange edge, which is a distance 2 from V, which connects 2 vertices, both being a distance 2 from V. So then, in this case here, we have a C3, and possible we had a C5. And we want to show that this can't happen in an extremal graph. Due to our weaker conditions, it's easy. We just can delete this one edge and replace it by 2 others by just connecting these 2 vertices with 2 new vertices. Because the two vertices are at distance 2 from V, it implies that every edge having V as an end vertex and these two orange edges can be connected with a path of length at most 2. So if the graph on top would be extremal, then the graph at the bottom would also be fine, but it would have one additional edge. So this implies that the graph on top wasn't extremal, so we do not have any edges between the first neighborhood of V and the so-called second neighborhood of V, which are all vertices that distance 2 from V. And we actually, with some case analysis, we can do the same and show that there are no edges in the third neighborhood. And so we are already close to a bipartite graph. And then comparing with some weight function on this already pretty structured graph, we can conclude. And with that, the C7 free case is proven. But then I want to ask one challenging question to end this talk. Can you find a better construction? So we actually conjecture that the construction which is extremal for among the C7 free graphs is the best up to one additional edge. And as long as a conjecture is not proven, one can try to disprove it or try to prove it. So that's a challenge you can do. And with this, I'm glad to finish the talk. Thank you all for your attention, solving the two cases with t = 1. And if there are any questions, I'm glad to answer them.
Thank you, Stijn. Let's all unmute ourselves and give a round of applause. So if there are any questions, just feel free to ask.
So do you think that there will, for general T, that there will be some nice form for it? Because the original question was also, it's an interesting question if there is a nice.
Yeah. So some of the results presented for t = 3 here can be extended to general T. So in particular, this bound is true where 3 is replaced by any k, as long if you, instead of C7, you take C2 t + 1. Or for example, for bipartite graphs. So then we can prove that the number of edges in the somewhat greedy tree is extremal. And for t = 3, 4, and 6, there are constructions from finite geometry where it's possible to attain the bound, and with a subdivision we can add one edge. Note, for example, when t = 2, the number of edges in such a tree is equal to delta squared. And so connecting some vertices will, or connecting some edges with the same vertex will exactly imply that you get the complete balanced bipartite graph. And so, for example, when delta = 2, it's just a C4, and then a subdivision gives a C5. But there we can do some blow-ups. If we do the same with t = 3 or larger, this is impossible. So
yeah, maybe just to make sure I completely understand, because you were saying extremal. So for if you sort of restrict to the class of graphs not containing the correct cycle, then you do know the exact answer.
Yes, for
larger T.
Yeah, only for 3, 4, and 6.
Oh, okay, yeah.
Because
so for large general T, it's not known to be, you have the upper bound, but you don't know if it can be attained.
Yes, that's true. And we guess that for at least some delta, it's also of the order delta to the T, but there might be a small difference. As was, for example, the case when delta is odd for t = 2, then the blown up C5 was not asymmetric, and you lose something, and maybe for larger T, you always lose something. And here, as is the case with the degree diameter problem, there are really big gaps between the lower bound and upper bound that are known.
But you would also expect that restricting to this class of graphs without these cycles, that the answer would be similar for the class of all graphs, or that there will be big gaps there?
Yeah, we think it's asymptotically fine,
Okay.
or good, but it's impossible to match the vertices precisely.
Yeah.
Because for t equals 3, 4, and 6, there are constructions, so you have projective planes and other generalizations which give the exact bound. Here it's not the case.
Are there any other questions? Okay, if not, I propose that we take a short break since we're a bit ahead of schedule, and we can resume with the next talk in, say,